So today I want to enter the basics of differentiation. So the first thing to understand is that integration and differentiation are absolutely essential for all topics that are forthcoming, not only in calculus itself. It has applications all over fields that apply maths. So even fields like biology, when you're calculating the rates of change, you will find a way to use differentiation somehow. So the first thing I want to do is give you the base definition of a derivative. Okay, so let's say we have a function fx. Fx can equal to any polynomial. Let's assume it's a polynomial in this case. Okay, and it is defined on an open interval. So I'm gonna label the interval I. Okay, and the bounds of the interval are ab. So this is the start of the interval and this is the end of the interval. Okay, and c, it's a random point on the x-axis, which is an element of AB, which means that C is somehow between A and B. So let's say we are deriving f at this point C. Okay, so at this point C, which is in the domain in which fx is defined, then we have the derivative, which is f apostrophe C. Okay, that's the that's how we write the derivative at this point, exact point C. So we're deriving this function at this exact point C. So the formal definition uses limits, which if you don't already know, I will cover in a later video. Okay, so the limit as a random variable h is h will not be in the final output. H is simply used for calculating the limit. So as h approaches 0, we have the function f c plus h minus fc over h. Okay, so if you understand the laws of limits, you will understand that whenever we have the h in the bottom and 0 substituted inside, we get an indeterminate form. So the challenge here is to substitute back inside fx and using the value of c and reform the equation so you can find a way to find the limit by substituting 0. Okay, so right now I'm going to simply erase this and I'm going to show you a sum. I'm going to show you a sum where we actually apply okay, now I'm going to show you a sum where we actually apply the formal definition. Okay, so we have fx. It's a parabola, so I'm going to give it 4x squared. 4x squared, okay? And we want the derivative of the function at x equals to let's say 2. At x equals 2, the point at x equals 2 obviously will be y is equal to 16. So at the point 216, we want to find the derivative of fx equals 4x squared. So the first thing I want to do is write in c is x, so c becomes 2. So f dash 2 is the limit as h approaches 0. The limit of h never changes, it's always 0. So c, which is 2 plus h minus f2 over h. We don't have a value for h yet. Okay, so let's substitute 2 plus h inside here by the basic laws of functions, which you should know. So that would be 4 2 plus h squared minus 224. 4 times 4 16. Substituting 2, and then we just put a h down there. Now let's break this up. So that's 4 plus 4h plus h square minus 16 over h. Break it up, 16 plus 16h plus 4h square minus 16 over h. 16h plus 4h square over h. Oh, 16h plus 4h square over h is equal to, we can simplify, 16 plus 4h. So since this is broken down, I'm going to find the limit of this reformed function. So the limit as h approaches 0 of 16 plus 4h, which if we substitute 0 inside 4h, we get 0. So 16 plus 0 is equal to 16. So 16 plus 0 is equal to 16. It boxed it for me. Okay, but there is something special about this 16. This 16 is not just the derivative of the function, it is the it is the slope of the tangent of this function at this point too. So I'm going to demonstrate an example for you. So let's say we have the graph, okay. I could draw 4x squared, but that would take a bit longer. So I'm just gonna draw y equals x squared. It's a simple parabola. Okay, it passes through the origin. Okay, passes through the origin, and this is the y equals x squared graph. Okay, so now let's take any point on the graph. Let's take 1. Let's take 2. Okay, fine. For the sake of this example, let's take perhaps 3. Okay, it is at this point. At this point 3. We can draw a tangent to the graph. A tangent is any line that touches this graph at exactly 1 point. So it's not straight. Let me give you a tangent. Oh, not straight. Okay, so this somehow only touches this graph at this point at x equals 3. Okay, so now let's say we're asked to find the slope of this tangent. Then all we have to do is find f dash 3. So we derivate the function, and then we substitute x equals 3 into it, and then we will find the gradient of the slope. So the thing about this parabola is, because the sides are all curved, the gradient at this point and the gradient at perhaps this point, so the slope would be, the tangent would be something like this. And do something like this. So the slope of this tangent and the slope of this tangent are completely different. So at every single point in this graph, the tangents all have different gradients, and the easiest way to find their gradients is using the differentiation method. So that's how differentiation just came about, but there's a whole bunch of applications with on.